So we're going to talk now about just using some shortcuts to find the zeros of these big polynomials so that we don't just have to do this giant list and check everything. And also what the point of the first lesson of this section was. So we've got this big fourth degree polynomial here, x to the 4 minus 3x cubed minus 5x squared plus 13x plus 6. And what we're going to do here is find all of the zeros of this polynomial. Yeah, to get any of these started, what we are going to want to do is list those potential rational zeros. So they're going to be plus or minus factors of the last term. Oh, actually, I guess for this one, since the lead coefficient is 1, I don't really even need to set up that fraction. So I'll just do, yeah, the factors of 6, right? Because it would be divided by the factors of 1, which is just 1. Yeah, so it's going to be that list, 1, 2, 3, 6. And so what we're going to do is plug them in till we find them. What I'm going to do, though, is just find 1. So just find, I'm going to write the word 1. I don't like the number there. Just find 1 0. So yeah, I'll try p of x, sorry, p of 1. And so I'll get 1 minus 3 minus 5 plus 13 plus 6. That's too big. P of negative 1 is 1 plus 3 minus 5 minus 13 plus 6. That looks to be too negative, yeah. P of, I guess I'll try 2. Don't have any of those ugly fractions for this one. So P of 2, 2 to the 4 is 16, minus 3 times 8, 24. Minus 20 plus 26 plus 6. So what do I have here? Minus 44. And that does look to be, I think, too large. Yeah, so I get 42, 48. Yeah, that one's not going to work. I didn't quite work out the exact number. I just knew it didn't work. So the next one, I'll get 16 plus 24 minus 20 minus 26 plus 6. This one might work. I get what? So 40 minus 20 is 20. Minus 26 is negative 6 plus 6 is 0. Yeah. So that one works. And so if you recall, what that tells us is that since x equals negative 2 is a 0, then x plus 2 is a factor. And so what I'm going to do is, yeah, factor that out. So I can use synthetic division for that. It's set up nicely for it. So I'm going to factor it out. And synthetic division, so I'm going to write my negative 2 on the outside, and then all my coefficients, 1, negative 3, negative 5, 13, and 6. And I always like to just indicate what powers those are. And do my synthetic division, so 1 is 1, 1 times negative 2 is negative 2. Add them together to get negative 5. Negative 5 times negative 2 is 10. 10 plus negative 5 is 5. 5 times negative 2 is negative 10. 13 minus 10 is 3, negative 6. And if I've done this right, because it should evenly factor out, we should absolutely get a 0 remainder. We need that 0 remainder. This doesn't really make any sense. And so this is going to tell us what the factorization is. So when we factor out the x plus 2, what we end up getting is x cubed minus 5x squared plus 5x plus 3. And so now we can actually just go through this again. What we're going to want to do now is try to pull out a factor from this smaller polynomial. So I have fewer options to work with here. So again, I'm going to do step 1 and list my new potential rational zeros. It's going to be a smaller set, so that's nice. 1 and 3, basically. So for this, I should know that 1 isn't going to work because 1 already didn't work in the previous one. You can try it though. It's not a big calculation, but yeah, 1 and -1 aren't going to work because they already didn't work. They didn't work in the big one, so they're not going to work in the small one. So P of 1 is not 0. P of -1 is not going to be 0. So yeah, we're just going to try the 3 and the -3. So P of 3, so that's going to be 27 minus 5 times 9 minus 45 plus 5 times 3 is 15, and then plus 3. That actually looks pretty good. Yeah, 27 plus 3 is 30, plus 15 is 45, and that'll cancel with the negative. Yeah. So same as before, I know that x equals 3 is 0. So x minus 3 is a factor. So again, I'm just going to factor it out. Synthetic division will usually work pretty well for you here. So I'll plug in my 3, all my coefficients, 1, -5, 5, and 3, and I'll run my synthetic division. So I'll get 1 times 3 is 3, 3 plus -5 is -2, times 3 is 6, plus 5 is -6, not 6, plus 5 is -1. Things were not going to go my way there. -1 times 3 is -3, adds to 0. Again, that 0 is super important because that means it does come out evenly, which is what we're hoping for here. So that's my constant, my x, and my x squared. And so now that tells me what I can pull further out. I get x plus 2. I can now also pull out an x minus 3. And then what's left is x squared minus 2x minus 1, which is coming from those numbers there. And you might notice actually, it kind of looks like that last term is a perfect square. It's in fact not. It's actually not factorable. Right? There's no two numbers that add to -2 but multiply also to -1. So what we could do here is the quadratic formula to finish this up. So remember that that is x equals -b plus or minus the square root b squared minus 4ac over 2a, where my a is the lead coefficient, b is the second coefficient, and c is the constant. And so we can actually write that out. So I've got x is -2, x is 3, and then this, using the quadratic formula, will be x is, my -b will be -2, so 2, plus or minus the square root of negative 2 squared. Maybe I'll actually just put the extra steps in here. Negative 2 squared minus 4, a is 1, and c is negative 1 over 2a. And I'll just clean this up. So that's 2 plus or minus root 8 over 2. And then 8, we can actually pull out the 4, the root 4, which is just 2. And then there's some cancellation here. So it finally ends up being 1 plus or minus root 2. So if I lump all of these together, I'm just going to write my answer over here on the left, because I'm almost out of space here. All of the actual zeros are going to be negative 2, 3, and 1 plus or minus root 2. So just because some of the zeros are not rational doesn't mean I wasn't supposed to find them. I told you in this question, find all of the zeros. So that ugly irrational one there with the root 2 is part of that set. Now, using the methods that I did in the previous lessons of just listing all of the rational potentials and plugging them in, you would have never gotten to those two solutions at 1 plus root 2 and 1 minus root 2. So actually, this technique of doing the factoring and reducing the polynomial is much, much better. So we'll do one more of these. All right, so for the other example, we're going to find all of the real zeros of this polynomial p of x equals 6x cubed plus x squared minus 1. So we do have a lead coefficient on this one, so it is going to be the kind of uglier set of potential rational zeros. But that's how we're going to start this. So on the top, it will be factors of 1, so just 1. And on the bottom, it's going to be our factors of 6, because that is the lead coefficient there. So 1, 2, 3, and 6. And so what we'll end up getting is this list plus or minus 1, a half, a third, or a 6. And step 2, find 1. All right, so yeah, I'll plug them in until I've got one. P of 1 is certainly too big. I get 6 plus 1 minus 1. P of negative 1 is negative 6 plus 1 minus 1. Too small. P of a half is going to be what? So 6 over 8, which is 3 over 4, plus 1 over 4 minus 1. That looks pretty good. Yeah, that's going to be 0. So I'm good with that. So what we get, that's x equals a half is a 0. So that means that, again, you could write it as x minus a half, or the nicer version is 2x minus 1, our factors. I don't like working with the x minus a half. You certainly can. I just really don't want to. It's going to make everything I do later much, much harder. So I'm going to stick with the 2x minus 1. That does mean that I'm not really set up very well for synthetic division, but you know what? I actually like long division better. So I'm going to factor that out using long division. Right, and again, the reason is that in the format 2x minus 1, I've got something attached to that x. The x minus a half would actually be suitable for it, but I'm not going to do that. Might as well get some more review with long division. So 2x minus 1 out of 6x cubed plus x squared. I've got a little gap there for my x term, and then minus 1. 2x, I've got to multiply by 3x squared to match the 6x cubed. And so I should distribute that through to get a negative 3x squared. And when I subtract the whole thing, 1 minus negative 3 is 1 plus 3 is 4x squared. There's nothing really to bring down. And I'll do the next one. So I'm going to need 2x times 2x to get 4x squared. Distribute it through to get a 4x squared minus 2x. And then 0 minus negative 2x will be plus 2x. Bring down my minus 1. And again, if I've done this right, there should be no remainder. And I know that 2x times 1 is what I need for my 2x. I should be able to see I get full cancellation here. Same idea. For this to actually factor, I need no remainder. But this does give me my factorization. So when I factor out the 2x minus 1, what I end up getting is that 3x squared plus 2x plus 1. Now I've got a quadratic, so I'm in pretty good shape now. So I could look to factor this quadratic using the old school techniques. I'm looking for two numbers that add to 2 and multiply to 3, and they don't exist. So again, on this one, I'm going to use the quadratic formula. So my zeros would be x equals a half, and then x equals negative b, so negative 2 plus or minus root b squared minus 4, a is 3, c is 1, over 2a, which is 3. And then if you notice, the inside of that is, the inside of that radical is not doing what we usually want it to do. That's 4 minus 12 is negative 8 over 6. So for our purposes in this course, we are going to reject that. If you do take a good chunk more math, or if you choose to learn about them, this is an example of what's called a complex number. Yeah, roots of negatives, but they're not real, and I did specifically ask for real numbers. So I don't want to say it doesn't exist. I should just say it's not real. And so we can just completely reject that answer. And so the only real 0 is at x equals 1/2. So quite a bit of work involved for these questions, but yeah, they are long, messy polynomials. There is actually sort of an equivalent version, or sort of not equivalent, but like kind of an extension of the quadratic formula for 3rd and 4th degree polynomials. It's this massive algorithm though. I one time used this algorithm to factor out a 3rd degree polynomial, and it was like 2 pages of written work. So I don't recommend ever actually learning how to do that. Anything that I hand you is going to have 1 or 2 kind of simple rationals or integers that you can pull out to hopefully reduce the thing. So yeah, that should be some nice tricks to make your life at least a little bit easier.